electrons. One electron will be stationary and the other one will fly, right? So we will have to find sort of the shortest distance between these two electrons. I feel like, yeah, I need to draw a picture. Right. So first, let me write, so we have two electrons. Right. So now we definitely have a different system. Here we have the system of a point charge and a capacitor. So point charge interacted with the charge capacitor. Now we have 2 point charges interacting. So the second system, which we discussed in today's class, right? When we introduced electric potential energy. So 2 electrons. All right, so the first one will be here. I'm just trying to estimate the space, the amount of space. So the first electron will be here, Q. And this electron, it's very important, it's stationary. The first, okay, maybe the second electron is shot from here. So that's my second electron, and it is shot with velocity v naught. All right. You know what? I will probably write values on the picture. So let me write it underneath. So v sub 0 equals to 1 times 10 to the power of 3 meters per second, 1 kilometer per second. So now let me explain why I wrote stationary. Because as these electrons travel, and let's say that was originally just at rest, of course they interact, of course they repel each other, of course this electron will be repelled and it will start traveling this way, changing its position, but we don't want that. Right? We don't want this electron to travel. So we demand that, I don't know, we nailed it, right? Or we hold it, right? So as that electron travels, this electron, for whatever reasons, is held stationary, basically artificially. You can hold it or you can nail it. So that is stationary electron. So given in the problem. So then what else is given? So at the initial position, at this moment of time, the distance between electrons is given. Right. So this distance is given. And let me label it as R1. Yeah. R1 is 1 millimeter. Yeah. Then, so electron, of course, travels because it has a large initial velocity. But at the same time, since it is going to experience force acting that way, because these two charges repel, of course, this electron is going to decelerate, slowing down, right? And most likely, after some distance, at some point, it is going to stop for a moment, turns around, and it will start traveling in the opposite direction, start traveling back. So let me draw this. So first it will travel this way, then turns around and starts traveling in the opposite direction. So this is a turning point, right? So what we need to find this shortest distance between two electrons. So let me label it. So that's what we need to find. Let me label it as R2 and let me put it question mark. So I can say that this is our initial point, right? And this will be my final point. And what can you say about the final point? It's a turning point, right? Which quantity will be 0? And again, it's not an acceleration. I remember a few classes ago, right, our conversation. So velocity will be 0, right? Velocity will be 0. That's the major feature of a turning point. Velocity 0, right? Okay, I will probably write that down. So V, which way I label it? I probably labeled V final, I still cannot see it. V final will be equals to 0. Okay, so I think that's what is given. Nothing else. Yeah. So what we need to find here are two. And again, two approaches. Now we have force approach from the past and energy approach. And like here, since energy approach is a new one and we're supposed to practice it, so let's start with the energy approach, and then once we finished energy, we will look at the force approach. So let me start with the second one again. Again, it's a kinetic energy in collaboration with potential energy under the roof of conservation of mechanical energy. So I can write conservation of mechanical energy. Yeah. E initial equals to E final. So that's the beginning. And now let's dive like over here. First write explicitly in terms of kinetic and potential energy, then, okay, one step at a time. So it will be K initial plus U initial equals to K final plus U final. And at this point, you need to remember which formula for the potential energy we have to use. Actually, in this problem, like based on my experience in the past on the final exam, on the exam, plenty of students, okay, not plenty, but I know a few percent of students, they just use the wrong formula. So when they get to this point, they just use this, which is of course not applicable over here. Right? So that is correct for a charge inside of a exposed to an uniform electric field. Here we have 2-point charges. We have completely different expression. K, Q1, Q2 divided by R, distance between them, between charges. Of course, now we have two, the charges are the same, so it will be KQ squared over R. Right? So in our case, U equals KQ times Q divided by R. So it's a K Q squared divided by R. So that's what we need to use. So careful look and pay attention to which system you're working with. Okay, so now actually I don't want to rewrite it one more time. So which term is 0? Final velocity is 0, so it means the final kinetic energy is 0. So let me dump immediately the final kinetic energy. So this is 0 because V final equals to 0. Potential energies are not 0 because you remember the reference. Where is the reference point? The reference point is at infinity. And during this motion, our charge is not at infinity. At this moment, it is at the distance 1 millimeter, and 1 millimeter is not infinity, right? So it means that, yeah, we need to deal with the rest of the terms. Here we will like it to dump 2 terms, there only 1. Okay, so now we can write explicitly. So this will be initial velocity is given, so 1 over 2 mv naught squared, then plus k q squared over initial distance r1 equals kinetic energy 0, then potential energy k q squared over r2. R2 is our unknown. Okay, let's look carefully in this equation and see if it's solvable. How many unknowns do we have in this equation? We have one equation, so how many unknowns? Given, 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 given are 2 unknown. One equation, one unknown. Problem basically is solved, right? So we applied all physics, so now we just need to solve it for R2. Right? So what I'm going to do, I'm going to divide the whole equation by kq squared, so that my unknown will be free of any factors. Right? You remember, you can multiply or divide each term of the equation by the same factor, and it will be correct. Right? So I'm going to do this. I'm going to multiply everything by 1 over kq squared. So pretty much it means that here it will be divided by kq squared, here divided by that, and this term will be divided by kq to the power of 2. Right. So 1 over 2 mv naught squared. Okay, let me do it this way. Divided by 2kq to the power of 2. This kq squared will just disappear. It will be 1 over r1, and this will be also 1 over r2. Okay? Because sometimes in the past students were confused when I do stuff like that, right? So what is that, right? No, it's just banal algebra. So now R2, in order to get R2, we just need to take this whole thing and dump it in the denominator on the right-hand side. So it will be R2 equals to 1 over, and I will just rewrite this whole structure. mv naught squared over 2kq squared plus 1 over r1. Okay, that's it. So that's the algebraic answer in the algebraic form. And now we just need to plug numbers. I'm not going to do it, but of course, you need to convert millimeters to meters, right? And calculate it carefully. I'm not going to do it. I will just write the answer, and it will be 0.34 millimeters. Okay, I converted to millimeters at the end. Okay, maybe I can write also in meters. 3.4 times 10 to the power of minus 4 meters. So that's the answer. Again, it's quite a deceleration from this velocity of 1 kilometer per second to 0 velocity within 0.6, okay, almost 0.6 millimeters, right? So this distance from this point to this point will be like 0.6, slightly more than that. Okay, so that's the energy approach. And again, in this case, it's reasonably easy. Yeah, you have to deal with more complicated expression for the potential energy, but it's not a big deal. Simple algebra. Now let's look at the force approach in this case. So let me put number 1 in the right. So now force approach, okay, which is based on forces and Newton's second law, and then we'll see. So let's do it. F equals mass times acceleration, right? And which force we have to use? Yeah, Coulomb's law. F equals k q squared divided by r to the power of 2, right? So of course I will just plug it there, and we will get what? Ma equals to k q squared over r squared, and from here of course we can get acceleration. It will be what? K square of the charge divided by m and r to the power of 2. At this point over here, you see, we used kinematic equations. Okay, kinematic equation, we used here kinematic equation. So now at this point, we're also supposed to start, okay, think about using kinematic equations. Can we use kinematic equations here? Okay, now I want you to look carefully and think, can we use kinematic equations now? You remember which test we have to run quickly in order to convince ourselves that kinematic equations is legitimate to use? That's why every time I write, if acceleration is constant, then yes, kinematic equations can be used. In our case, is acceleration constant? No way. We have r to the power of 2 in the denominator. Yeah, k constant, q constant, m constant. R is a variable. As this electron approaches closer and closer and closer, r becomes smaller and smaller and smaller and smaller. R changes. So it means that acceleration changes as that electron travels. Kinematic equations, we cannot use kinematic equations. It's illegal, right? So we would be criminals from the mathematical point of view, right, using kinematic equations in this case. See that? Yeah. So let me use red. So it's not equals to constant, and as a result, kinematic equations cannot be used. Kinematic equations cannot be used. Okay, of course I need to express my emotions. Of course it's a sad face, right? Kinematic equations cannot be used. But so what can be done in this case if kinematic equations cannot be used? So what's the approach? Not a big deal. So we just need to use Newton's second law, which is effectively second order differential equation. So we will have to just use what? Acceleration. It's a second derivative of r. Here we'll have mr double dot, and force kq squared over r squared. So you'll have to just solve second order differential equation. So what we have to do in this case, actually, so it will be mr double dot equals to kq squared over r squared. Solve second order differential equation, right? So which is of course significantly more complicated. Okay, so let me write second order differential equation, right? And of course I can put even bigger set phase. So in this case, no doubts, energy approach is easier. And again, it's not a big deal. Yeah, it can be solved, right? But in comparison with the energy approach, this is painful.